All right, guys, working on 7.5. It's really an extension of 7.4. Some textbooks put them together. Just a couple different types of trig equations to work on here. Example 1 here says, find all the solutions to the equation. It says, notice that it looks quadratic in form, however, the variable or trigonometric terms are different. So we must substitute using identity before factoring. So this would be like something, if I had, like an x squared plus 3x plus y equals 0, where I don't know what that is, I wouldn't know how to factor this. So we run into an issue because we have two variables here. So that's kind of really what's going on here, is that we've got two variables. We've got a sine of theta and we've got a cosine squared theta. And that's problematic. So what we want to try to do is, if possible, substitute one of these, okay? And usually what you're going to do is you're going to look for the one that is of a higher degree. So the cosine squared obviously is a higher degree, because that allows us to create the substitution that is recognized here. If I go ahead and move over the sine squared, so you see now maybe the purpose of working with these identities initially in 7.1 and 7.2, because now I know what cosine squared is. Alternatively, it's this. So now I want to have, so we're my equation over here, 1 plus sine of theta equals now 2, and now this turned into a quantity, so it's going to be 2 times the quantity, 1 minus sine squared theta. Okay, just kind of do the algebra that is here, take that 2 through, so 2 minus 2 sine squared theta. Now it's just a matter of getting everything on one side, because now it's quadratic in nature, so I'll add 2 sine squared to both sides. We'll have then plus sine of theta, and then when I move that 2 over, it'd be minus 1, equals then 0. So we've got a quadratic here. It's the AC method. I'm going to let sine of theta equal u, so I can rewrite this thing then as 2u squared plus u minus 1. We're looking at -2, so that's obviously 2 and 1, and it's going to be a -1. So I'm going to rewrite this then as 2u squared plus 2u minus u minus 1. Group the first two, so it's going to look like 2u, u plus 1, minus 1, and then u plus 1. So that's just the AC method. So then we've got 2u minus 1 will equal 0, and u plus 1 will equal 0. That's going to lead us then to u equals 1/2, and u equals -1. Now you just got to remember what u was. U was sine of theta. So sine of theta is 1/2, and sine of theta is now -1. So we're going to ask ourselves, when does the sine of theta equal a positive 1/2? Okay, so thinking about my unit circle, where does the y value become 1/2? Okay, on that unit circle. And it's going to be about right there, which is the theta of pi over 6. So theta equals pi over 6, but it's also y equal 1/2 right there. So that is 5 pi over 6. Okay. Now this question doesn't talk about it, but if we wanted to go the infinite number of solutions, we would then obviously add 2 pi k to that, and 2 pi k, where k is an integer. Okay. Here we want to know when sine of theta is equal to -1. Well, there's only one place that sine of theta is equal to -1, and it's right there. Theta equals 3 pi over 2. So I'm going to look at this graphically real quick. if we remember the concept that no matter what equation you have, as long as you take the left-hand side and let it be a function, take the right-hand side, let it be a function, where they cross is, as an x value, is the solution then to that equation. So I'm going to go 1 plus sine theta. 1 plus sine theta. And obviously got to use x here. So that was the left-hand side. I'm then interested in the right-hand side, which was 2 cosine squared. So 2 cosine squared x. Looks like that. Okay. And now we're looking for where these two things intersect. Okay. Well, if I take, let's go ahead and put my axes in terms of, instead of pi over 2, let's go pi over 6. And it just creates, so all these vertical lines then are pi over 6, or multiples of pi over 6. So we see here this first one right there, they're crossing at an x value of pi over 6. We go to the next place where they cross, and this would be 1, 2, 3, 4, 5 lines, so that's 5 pi over 6. Those are the two values that we came up with from the sine equaling 1/2. Keep going over here. Try to zoom in here real quick. And we see then that this one here, where they're the same again, is at 3 pi over 2. So that's hopefully demonstrating to you that concept. Now, if you want to look at this version, if you want to go 2 sine squared x plus sine x minus 1, if we look at the purple one, now we'd be looking at where this thing crosses the x-axis, because that's essentially within the right-hand side, or the right-hand side function in the equation. And again, if I've got things in terms of pi over 6, and I zoom too far out, we will see, let's see here, graphics, x-axis, pi over 6. There we go. Again, we're across the x-axis at pi over 6. We cross at 5 pi over 6. And we end up being tangent at 3 pi over 2, but it's still equal to 0 there. Just a couple different ways you can kind of interpret those solutions or find those solutions graphically. Let's go down to this next one. So here's an example where I finally put in the where I've put in the restriction on how or where I want your solutions to show up. So it says between 0 and 2 pi. Just give you a little introduction to the question. It says this equation incorporates sine x and cosine x, but it says both are raised to the first power. Okay. If you think about all our substitutions, they're much easier to do when the power is 2. Okay. So the question is, do we have an operation that can create a power of 2? Okay. And if you think about that, we do. We can square things. And if you remember back to college algebra, when we square things, what happens is that you create extraneous solutions. So that's something to think about as we complete this problem. Okay. So what I'm going to do, I'm going to take this left-hand side and square it. So it gives me cosine squared theta plus then 2 cosine theta plus 1 equals then sine squared theta. Okay. Now making a substitution, because we have cosine squared and sine squared, you could ultimately get rid of either one of them. But if I were to get rid of this one, if I was to replace this one with like 1 minus sine squared, it would mesh well with this, but I would still have a cosine. And that's a problem. It'd be the same problem that we had in the last example. So in this case, what I want to do is I want to replace that with 1 minus cosine squared theta, because now you see that everything's in terms of cosine. Now move everything over. So the nice thing here is that when I move the cosine squared over, it gives me 2 cosine squareds. That one and that one are going to cancel each other out. So it gives me 2 cosine theta and 0. Okay. So now this is like a nice one to factor because it's 2 terms. This is like if I let cosine be u, it would be 2u squared plus 2u. So I can just factor out a GCF. And that GCF in this case is going to be 2 cosine theta. And I'll be left with cosine theta plus 1 equals 0. So then 2 cosine theta will equal 0, and cosine theta will equal -1. Okay. So this one, this set here, I know I skipped some algebra, but it came from that factor. All right, so divide both sides by 2, it gives me cosine theta is equal to 0. So now I got to just think about the unit circle. When is the cosine equal to 0? Well, for the unit circle, that happens at theta being pi over 2 and 3 pi over 2. And here the question is, when does cosine of theta equal -1? Well, so when is the x value of -1? That's going to be at pi. So those are my potential solutions. Okay. Now, what I actually have to do is check those, because I squared something. This is something that's always got to be in the back of your mind when you square things, is that potentially these could be, some of these could be extraneous. So what I'm going to do is I'm going to figure out, okay, if I go cosine of pi over 2, cosine of pi over 2 plus 1, does that equal the sine of pi over 2? So cosine pi over 2 plus 1, does that equal the sine of pi over 2? Well, cosine of pi over 2, that's 0, plus 1, does that equal sine of pi over 2? Sine of pi over 2 is 1. Is that true? Yes, it is. So pi over 2 is a solution. Now I'm going to try cosine of 3 pi over 2 plus 1, does that equal the sine of 3 pi over 2? So cosine of 3 pi over 2 is 0, plus 1. Sine of 3 pi over 2 is -1. Are those equal? Does 1 equal -1? No. So that's extraneous. And then I'll try cosine of pi. Cosine of pi plus 1, does that equal the sine of pi? Well, cosine of pi is -1, plus 1, sine of pi is 0. Does that end up being true there? It is. So those two are my solutions. And those two are then inside that interval, so I don't need to do anything else within that problem. Okay. If you want to, again, look at really what we're doing here graphically. See if I can set this up. 2 graphics. Let's go x-axis, distance, pi over 6. All right, so when we type in what we started with, and I'll put this in the blue one, we'll go cosine of x plus 1. Where does that equal sine of x? Okay, so that gives us these 2 curves. Let me zoom out a little bit. That gives us those 2 curves. Okay, and you can see that we're getting pi over 2 as an answer and pi as an answer. Okay, but when we square things, okay, so we square things, and I'll look at what the squared version over here looks like on the yellow, and it would essentially be this. It'd be cosine of x plus 1 squared. Where does that equal sine squared of x? Okay. Now over here, you see the intersection at pi over 2. You also see the intersection at pi, but now you see the intersection at 3 pi over 2. So when we square something, we generate a situation where these curves could potentially intersect more times, okay, than what the solutions to the original equation should be. You remember what we talked about in college algebra is that all of the solutions to this, because this is what we were looking for, all the solutions to the equation in the blue reside as solutions to the equation here in yellow, okay? But that does not mean that all of these solutions are the same as those solutions, okay? There could be extra ones in here, and it's all because we squared things. Scrolling down to the next one, says equations that involve multiple angles. So now we're thinking about things like sine of 2x, sine of 3x, cosine 10x, and anything in which essentially that number there, which remember back to transformations, that's your b value. And when that b value is bigger than 1, what this does is it actually compresses things. So this thing is going to isolate or oscillate more times between 0 and 2 pi. So what's going to happen is we're going to get more solutions. All right. It says when solving trigonometric equations that involve functions of multiple angles, we first solve for the multiple angle of the angle. It says then divide to solve for the angle. I know my notes say here I'm going to show you 2 processes. I'm going to stick to one. I'm going to stick to the easiest one. So this is how we do it. We essentially just solve for 3 theta here. Okay, so we're going to go take 2 sine of 3 theta minus 1 equals 0. So when solving this, we're going to just try to isolate the sine of 3 theta again. So add 1 to both sides. 2 sine 3 theta is equal to 1. Divide both sides by 2. So we get sine of 3 theta is equal to 1/2. And now the question is, so normally we would say, when does theta equal 1/2? Well, now I'm going to ask the question, when does 3 theta equal, or sine of 3 theta equal 1/2? Okay. The way we do this is we still think of our unit circle, and we think, okay, well, at pi over 6, the y value is 1/2. So I have 1/2 here. Okay. But it's also at 5 pi over 6. So 3 theta is equal to 5 pi over 6. Okay. Now what we've done here is we've developed a thing that is equal to 3 theta. So if I take 3 theta is equal to pi over 6, put pi over 6 in right there, make that substitution, and you get sine of pi over 6, that does equal 1/2. But remember when we do this, that this would be like an equation, like if I had, just make an analogy to, like if I had 5 plus 3x equals 12, you'd have 3x is equal to 7. You don't stop there, okay? But that's kind of where we're at right now. We have 3 times our variable is equal to something. Here, you would divide both sides by 3 to solve for x. That's essentially what we're going to do here, okay? Now, the only thing that I want us to be aware of is that usually they're going to ask you to find answers between 0 and 2 pi. So the best way of doing this is before I divide by 3 here, I'm going to add my 2 pi, okay? And I'm actually going to divide that by k. Okay. And you'll see why here in a little bit. And then here in the same one, I'm going to take 2 pi. I'm going to divide that by k as well. Okay, and I'm going to say that k is an integer. Okay, k is I'm going to start. Basically, k is our counting tool here. So I'm going to let it be 0, 1, 2, 3, and see what happens then when that's the case. Okay. All right, so when I do that, I've actually made a mistake here. I don't know why I wrote it this way in the notes. It's going to be 2 pi. I'll write it this way. 2 pi over our b, which in this case will be this number 3, and then times k, and then k is 0, 1, 2, 3. So I apologize for that. So this is going to be, and maybe it makes sense just to just add 2 pi initially. All right, so just side note, Gorilla here. My daughter has been using my tablet to color on here, and that's got a button on here, and if I push it, it cuts and pastes. So that's the last thing that we cut and paste. So that's why that showed up. Sorry about that. So now I've got this, okay, and I'll go ahead and put my k here as well. So what's going to happen now if I solve for theta, divide everything by 3, so it's going to be pi, or not pi, theta is equal to, now I don't like to divide by 3 in these cases because I've got a fraction here, so I multiply by 1/3. So I get pi over 18 when I multiply by 1/3 here. And then when I multiply this by 1/3, it gives me plus 2 pi k over 3. And then I'll do the same thing down here. Multiply by 1/3, so it gives me 5 pi over 18 plus then 2 pi k over 3. So now what we do is we allow our k to be what we call kind of our index or our counting tool here, because right now those are only solutions between 0 and basically 2 pi over 3. We want to go all the way around to 2 pi. So we're going to let k equal 0, then we'll let k equal 1, and then we'll let k equal 2. And you always stop one short of what that number was with your k term. Okay, and this essentially gives me the 3 different intersections that if we were to graph this, we generate when we compress our graph. So now it's just a matter of plugging in k and evaluating. So you get pi over 18 plus, if k is 0, this goes to 0. So pi over 18 is my first answer. Then when k is 1, so this becomes a 1 here. So I've got pi over 18 plus then 2 pi over 3. And remember, so adding fractions here, I need a common denominator. So I'll multiply the bottom by 6 to get 18. So multiply the top by 6 to get 12 pi. And then add the numerator. So I get 13 pi over 18. Now the next thing is to put k as 2. And you can do that exact same thing I just did. Or you can say, you can see a common, this is basically an arithmetic sequence. So you can see the common difference here as being 12 pi over 18. So then if I add 12 pi over 18 to this one, I should get 25 pi over 18. And that's one grouping of solutions. That's what my theta should be in one revolution so far around the unit circle. Okay. Coming down here, we're going to do the same thing. We'll let k be 0, so we got 5 pi over 18. That's when k is 0. If k is 1 again, I'm going to be adding 12 pi over 18 again. So in that case, I'm going to have 5 pi over 18 plus 12 pi over 18, so 17 pi over 18. And then this one here will be another 12 pi over 18, so 29 pi over 18. Okay. I don't know. I want to see if Desmos It's probably not going to, but see if Desmos offers a graphical here that makes this a little bit easier to see than GeoGebra. But I'm going to type in 2 sine of 3 theta, or 3x minus 1. We'll put us in radians. And I'm hoping, I don't, if this doesn't work, we'll go to GeoGebra and actually do it. But if I click on this, let's see. Okay, it does give me the radian measurement for my solution. So the first one here, you see pi over 18. Okay, then I'm going to skip one real quick, and I'm going to come to that one, and you get the 13 pi over 18. I'm going to skip one more, and I get to that one, and it's 25 pi over 18. Okay, I think maybe it makes sense here to kind of show you if I have x equals 2 pi and x equals 0. Really what we're doing is trying to look inside those two vertical lines there. That's the distance of 2 pi. So that's one revolution around the unit circle. And right now we're seeing those three solutions that came from ultimately this here at the pi over 6 mark. Okay. Then we see that 5 pi over 18, which was the first solution in that second line. Skip over to that one, there's 17 pi over 18. Then skip over to that one, and there's your 29 pi over 18. Okay, so Desmos is nice in that regard, that it's something that doesn't always give me those real nice results there for my theta, but in this case it did. But kind of comparing that then to our traditional sine of x. If I compare it to my original sine of x, and I'll make it 2 sine of x as well, just to see that the amplitudes are the same. And I'll subtract 1 from it so that they're shifted the same. You see here, with just that purple one, okay, in between these two vertical lines, which denote the period of 0 to 2 pi, you see you only get 1, 2 solutions. Okay, so what does this 3 ultimately do? It takes the number of solutions that we had and it essentially triples it. So let's see if I can do this. Let's put an A here, create a slider for A, and let it only be moving by steps of 1. So we can see now that when I move that A to now 2, so this would be 2 sine of 2x, we have more solutions happening inside because we squeeze that graph down. And then we get to 3x, we squeezed it down. Okay, and you can maybe even see that a little bit better if I go back and remove the step on that, and you can actually see it more kind of visual as it's getting compressed. You're seeing more solutions getting pushed into that 0 to 2 pi interval. All right, so come down here. This is the same situation. It's just a instead of a multiple, it's now half. So this is going to really work the same way. We'll just kind of run through this and make comparative remarks about this one. So we got radical 3, tangent. Now it's theta over 2. Is equal to 1. When I move that 1 over, I'll divide both sides by radical 3. So we get tangent of theta over 2 is equal to 1 over root 3, which turns into radical 3 over 3. So now I've got to figure out where does that happen for our tangent function. Okay, So remember, tangent is sine divided by cosine. So at that position right there, it'd be radical 3/2 over, or comma 1/2. So take 1/2, my sine divided by my cosine. That will indeed give me that one there. Okay. Kind of a quick way to remember this. If you remember, so the tangent is only going to give you either radical 3 or radical 3 over 3. And it's going to happen at one of two spots, either the 30 degrees or the 60-degree spots. I remember that radical 3 over 3, it has more 3's in it, and 30 degrees has more 3's in it than 60 does. So I remember that those two go together. If you want to use that, you can. You don't need to, but so I know that this is going to happen at pi over 6, okay? But it's also going to happen down here, okay, at 7 pi over 6, because it's got to be positive. It's got to give me a positive result. So then I need a negative divided by a negative. Okay, so theta over 2 at 7 pi over 6 as well. So I'm trying to give myself some more room here. So my theta over 2 is equal to pi over 6, and theta over 2 is equal to 7 pi over 6. Okay. We're then going to add to it our period times k, and then our period times k. Okay. I'm going to now multiply both to solve for theta. I'll multiply both things by, everything here by 2. So I get theta is equal to what's going to end up being, if I double that, it gives me pi over 3 plus then 2 pi k. And then here, I'm going to get, so if I multiply by 2, it's going to count 7 pi over 3 plus 2 pi k. And the only thing here now is, k can still be 0, 1, 2, whatever you need it to be. But you got to pay attention. This isn't as easy as the last one to determine where I stop with our k's. You're going to have to pay attention to what your what WebAssign tells you. If they say between 0, let's say 0 to 2 pi, okay, well, if k is 0, then that will give me pi over 3, so that'll be a solution. But if k is 0 here, that gives me 7 pi over 3, and that is already beyond that right there. Okay. If they would have asked me to find an answer between 0 and like 4 pi, then I would say, okay, well, that one's going to check because it's between 0 and 4 pi. But now if I look at this one, when k is 0, well, that works. So that would be a solution between 0 and 4 pi. Then I would say, okay, well, what if k is 1? Does this one give me a solution between 0 and 4 pi? And if k is 1, it does. That actually gives me 7 pi over 3, which is that answer there. So you just gotta kind of work with it and substitute k values and get a result and see if that result meshes with the restriction that they're providing you for ultimately the domain for your answers. Okay. So let's go ahead and take a peek of this on Desmos or GeoGebra. Let's use Desmos again. So we are looking at, we have square root of 3, tangent of theta over 2, minus 1. So we're looking at where this thing crosses the x-axis. So we see it happens once at pi over 3. The next one is 7 pi over 3. Next one then would be 13 pi over 3 when that k value ends up to increase. Let's look at how that compares to the square root of 3 tangent of just x minus 1. You can kind of see that if we look at, let's just look at between negative pi over 2 and x equaling pi over 2. Remember, that there is the period for our tangent function. Okay, when we end up multiplying the x by a number between 0 and 1, which in this case obviously shows up as division, what happens is that it actually kind of pulls our tangent function horizontally. It's a horizontal stretch. And in this case, it doesn't stretch it far enough to where that point right there leaves the set of asymptotes, but it does stretch it and pull it further to the right than what it was when it was just a 1x. Okay, so the algebra that we go through is effectively demonstrating how much it needs to be pulled to the and in the horizontal direction when we multiply by that 1/2. Again, if we want to put, like if I put a here as my divisor and then show, well, what happens when that a starts to increase, you can start to see how the red curve is being stretched. It started as the green curve. The green curve is getting stretched horizontally. And when it gets stretched horizontally, we are kind of moving that intercept horizontally as well. Okay, something that you'll see in regards. So let's take a let's just take sine of x real quick, and let's look at it between 0 to 2 pi. Can I do that? I'm not sure. Maybe I do it this way. 0 to 2 pi. Well, there is a way. There's a notation to get this to show just that domain that I want, but I can't remember the commands for it. So let's just go to GeoGebra. Sorry about that. If we look at just the sine function, so if having some technical difficulties here with my keyboard again. Don't know why that fixes it, but it fixes it. So graphics. All right, so if I look at just the, still having problems. Okay, so all I've done here is I've just graphed sine of x, and I'm just trying to focus on looking inside of one period, okay? If I then compare that to sine of, let's just say, b times x, as we create a slider of b, obviously when b is 1, it's the same graph, but now let's look at what happens when we move this b value to a number greater than 1. And you can start to see that that green curve, right now that green curve, if we're looking at like x-intercepts, we've got 1, 2, 3 here. When this goes to 2, now we've got 1, 2, 3, 4, 5. Okay. And we keep going, and we see that that kind of just, it compresses and gives me more solutions. Okay. Well, when I go the opposite direction, instead of making it a number bigger than 1, let's make it a number between 0 and 1. So let's go to 0.5 like the last one did with the tangent. Now you see that we've pulled that function apart, and now stretched out, it doesn't intersect the x-axis as many times inside that yellow region as it did when it was just sine of x. So that's, and we can get even kind of more severe with it. In this case, we don't get any intersection other than at the 0.00, when we have a 0.2 as my multiplier there for x. So that's kind of what's happening when we were looking at the sine and cosine functions, and why when the number in front of your x, the b value in front of your x, when it is larger than 1, you're going to get a lot more solutions than you traditionally do. When it's between 0 and 1, you're actually going to get a lot less solutions than you usually do. Let's kind of keep working with some examples here. So solve the given equation. It says enter your answers as a comma separated list. It says let k be an integer. Round terms to 3 decimal places where appropriate. If there's no solution, enter no solution. So these are, tell you what, let's do this. All right, so those are some, we got two more examples. I want to come up with I'm going to go to WebAssign and just pull off some more multiple angle questions. And I'll practice some of those with you here. And I'll save those last two examples for the next session. Here's a question that is in your homework, similar to what's in your homework, where you look at this, you say, okay, this is going to be a multiple angle formula. However, multiple angle formulas, or I guess multiple angle equation, they all have to be the same. So every time I see a 2 theta or an argument, it's got to be 2 theta and 2 theta. And that's, in this case, I don't have that. So when that happens, you have to somehow get them to be the same. Okay? And there's only one way to get them both to be the same. It's to use this approach that we talked about in one of the previous sections, that the sine of a double angle, sine of 2 theta, is the same as 2 sine theta cosine theta. Okay. Now, generally speaking, when I make a substitution, I don't want to bring in a new trig ratio, but if we do that here, it shouldn't turn out to be too big of an issue. So I'm going to replace sine of 2 theta with 2 sine theta cosine theta minus then the 6 sine theta that's already there equals 0. If I distribute the 5, it gives me 10 sine thetas cosine theta minus 6 sine theta is equal to 0. And the reason this one works this way is because now we have two terms here, and there's a GCF of a 2 sine theta that we can bring out. I'm going to divide this by a 2 sine theta. It gives me 5 cosine theta. I'm going to divide this by 2 sine theta. It gives me negative 3. So now I've got a product of two factors gives me 0. So it means 2 sine theta is equal to 0. And it gives me 5 cosine theta minus 3 is equal to 0. Solving both these for sine of theta, this one give me sine of theta is equal to 0. This one here give me cosine of theta is equal to 3/5. Okay. This one's not bad. We know sine of theta is equal to 0. The y value is 0 at theta being 0 radians, or theta being pi, or theta being 2 pi. Okay, now I'll go back in a moment to WebAssign and see if 2 pi is going to be something they're looking for, because if you remember, that one and that one are coterminal. So a lot of times they'll probably say, like we said, 0 to 2 pi like that, because these two answers are essentially the same spot. But now the cosine of 3/5, that one I don't know. Okay, cosine of 3/5, we don't know that off the unit circle, so this is what we got to do. Where 3/5 is 0.6. So if I'm thinking about the unit circle, I'm looking at an x value of about, so there'd be an x value of about 0.5, so 0.6 is maybe there. So I'd be looking on my unit circle at essentially those 2 points, because those are the ones where the x value is 0.6 or 3/5. So the only way that we can do that is with our calculator. So we're going to go, let's see here, get Desmos up. Do it in radians. So it's going to say, we're going to go arc cosine of 3/5. It gives me 0.927 radians. 0.927 radians. So that position there would be 0.927 radians. Okay. Now this here would be negative 0.927 radians, but we don't like a negative. So the way that we change that to make it positive is add 2 pi to it. So I'm going to take, there's other ways of doing it, but here in Desmos, I'm going to take negative arc cosine of 3/5. So that's the negative 9.27 and add 2 pi to it. So it's going to be 5.355. 5.355. 5.355 radians. Okay, so those are my two solutions now for theta here with this cosine. So it's 0.927 radians and 5.355 radians. But it wanted the infinite number of solutions. And I don't think I've rounded to the right number of decimal places, but you guys can figure that out. If it wants infinite solutions, then I'm going to add 2 pi k to all of these. Okay, and here's a thing to think about. If I add 2 pi k to that one, it's going to be the same as this one. So, this one will generate 2 pi, so will this one. This one will generate 4 pi, so will this one. So they're the same thing. And then here I'm going to add 2 pi k and 2 pi k. I'm going to go back to WebAssign, take a peek at that real quick. You see that the 2 pi k plus 0.9271, we get 2 pi k plus that one, and we also get pi k. Now, I don't think you're going to be wrong by typing in what we had, okay? But think about what is, and when we look at these here, your solutions, if, let's just say k is 0 for this one. If k is 0, then you get 0. If k is 0 here, you get pi. And if k is 0 here, you get 2 pi. So what is another formula that will generate the same results? A more simple formula that's going to reproduce the same results is pi k, where k is an integer. On a test, handwritten test, guys, I don't care if you write all three of those. They are redundant and they can be better classified as just pi k, but it's in my opinion kind of a minor detail to rewrite that way. You get into further like calculuses and stuff that use this stuff, maybe that will be preferred, but right now I'm not too concerned about it. If you answer things like this in WebAssign, because I'm not sure if it'll count wrong or not, I don't think it would, but it might. If you go and answer it and you've done everything's right, but it's giving you the feedback that something's amiss, think about if these equations can be better written or condensed as like this one is pi k. Let me pull up another one here in a moment. All right, so taking a look at this one here, you see in this case it is a multiple angle situation. So So I'm going to just kind of isolate that secant of 3 theta, which is then going to give me obviously 2. And now we have to decide, okay, so when does the secant of 3 theta equal 2? I'm not a big fan of working with the secant, so what I like to do is say, okay, and so this is essentially a proportion, okay? And if a rule about proportions is that you are allowed to take the reciprocal of the left-hand side as long as you take the reciprocal of the right-hand side. Okay. Well, if we remember through our identities that 1 over secant is the same thing as cosine. Okay, so when I see secant or cosecant or cotangent even, and I've isolated it, and I'm trying to figure out what, secant, cosecant, and cotangent, where they evaluate at, like in this case 2, I don't do that. I always look at the reciprocal. Because I think it's easier to figure out where is the cosine equal to 1/2. And what that does for us then, remember we're going to solve for 3 theta here. Where's the cosine equal to 1/2? Unit circle, cosine is at 1/2, right there at pi over 3. And then down here again at 5 pi over 3. Those are your 2 spots. So pi over 3 and 3 theta equals 5 pi over 3. Now, if you remember, we're going to add to find our infinite solutions, and that's another way of saying is find all solutions. I'm going to add the period times k, and the period times k. All right. So now, to solve for then theta, I'm going to divide both sides here by 3. So I get theta. So pi over 3 divided by 3 is pi over 9. 2 pi k divided by 3 is 2 pi k over 3. Okay. And then this one here, I will get theta divided by 3 again, be 5 pi over 9 plus 2 pi k over 3. Okay. So you get there's the first one, there's the second one. Okay. Now, part B is the situation where they ask you, okay, find all of your solutions between 0 and 2 pi. Well, that means if I go k is 0, 1, or 2, okay, I will find all my solutions. If k was 3, it will put me outside of 2 pi when I start with pi over 9 and add then what would end up being 6 pi over 3. So pi over 9 plus then 2 pi essentially will put me outside of 2 pi. So that's why we always stop 1 short of that number right there. We start at 0 always, stop 1 short. So when I'm at 0, obviously this first one's going to be pi over 3 when that k is 0. When k is 1, okay, I'm going to have pi over 9 plus 2 pi over 3, but 2 pi over 3 with a common denominator is 6 pi over 9. So that's what I'm essentially adding each time here. So that's my common difference. So 6 pi over 9 added to pi over, oh, sorry, I don't know why I put a 3 here. It's pi over 9. So I add 6 pi over 9, gives me 7 pi over 9. Add another 6 pi over 9, gives me 13 pi over 9. Down here, first answer is 5 pi over 9. Add to it 6 pi over 9 gives me 11 pi over 9. And then add 6 pi over 9 to that, it gives me 17 pi over 9. And remember, that's the process of essentially taking our, where we work a cosine function between 0 and 2 pi, and it's going to now, between 0 and 2 pi, it's going to happen many more times, okay? And that's why we get, 1, 2, 3, 4, 5. I'm missing one more, so it should be one more going through there, but it gives me ultimately these 6 solutions instead of just these 2. So that's something to look at there. Um, you can check these. Obviously, you can always check these. Take these numbers. Take pi over 9 on your calculator. Go secant 3 times pi over 9 minus 2. Hit enter. Does it give you 0? Absolutely will. So that's an alternative way of checking. All right, I'm going to go ahead and stop with that one. I think the next session on Monday, I'm going to continue with doing, like I said, I'll come back to these 3 examples or 2 examples. We'll start off with those, and then maybe run through some more of these. Hopefully, maybe by then, I've got some questions that you guys have asked, and maybe I can put a quick video together with explaining some of those. Keep me posted with questions, guys. Some of you are doing that on a regular basis. Some of you have not heard from yet. Do not hesitate to reach out to me. Have no problem inserting those questions into these videos or making separate videos. So please do those things.